of our chest, you know. And so I've got the counterbalance weight, which is just the bismuth, which is diamagnetic, but that's not really affecting anything. So that doesn't really affect anything with the magnets near it. Obviously it repels magnetism, but so I rebalanced in the previous live stream. I was talking about repositioning some steel shims in between the magnets and the end arrays to basically reduce the amount of entry, repulsion and exit attraction to prevent the stalling of the rotor assembly. Now with the rebalanced segment, I can just give this magnet a little push each rotation, which is not much, to maintain rotation, because the segment is working much better. Now obviously if I had more than one segment, which is why I'm waiting for new magnets to arrive in the mail, which I don't know when they're going to get here, probably up mid-August, and I'm kind of eager to, I'm quite I just can't wait. You know, well, I want to be able to build another segment the same as that one and have one on each side, because even when the magnet is in the inside, it will spin. Look at that. That is pretty impressive. I only just put the magnet there for a second, like. But what's interesting now is if I do that, if I bring the magnet in and start this thing to rotate and just give it a nudge each time, it will keep going. I'm nudging the magnet just a fraction and it will keep going. Look at that. I mean, that is, I didn't get that before. You see this? I'm just nudging it on the outside perimeter and it is literally, it keeps going. I couldn't get it to do that before. So that is one hell of an improvement in the fact that now the array is doing more to accelerate. You can see the acceleration point at that point, just there, right there, right? It has a bit of a kick and I can feel it on the magnet. So we're on the disc, on the rotor disc, and I'm not moving the magnet around with the segment. All I'm doing is just giving it a little nudge, because if I just hold it still like this, I can feel a kick, and you see it kicking. Well, but it will stop because there's still a certain amount of rejection on the entry point. It's a tiny amount of rejection, but not much. So what I'm saying here is that we have a situation now where this thing is much more attuned. The rejection, you can see it when it's coming this way. Look, you can see where it stalls when I do that. So that is a tiny amount of rejection. That is not really a significant problem. So let's get this thing moving. Oops, I don't want to be too close, otherwise I'll stick to the steel, because the steel is still a problem. We still have a problem with the steel. Let's get it moving again. So this magnet is literally, I mean, this magnet I'm holding in my hand is, I'm not even using the array with the U bracket. All I'm doing is giving it a little nudge. So imagine if this thing was pivoting on, imagine if this magnet that I'm holding in my hand was pivoting on an actuator. The forces I'm feeling wouldn't repel against the, well, it wouldn't be an equal opposite reaction anymore, because the forces are actually would be diverted to the actual part of the pivot point, which would be which wouldn't influence the actual direction that I'm rotating the magnet. You know what I mean? So what I'm trying to say is the angle of the magnetic field would be such that it wouldn't reject the amount of force required to turn this magnet, because the forces would be at, can't really show you this. If you have an equal opposite reaction, let me get a piece of paper a minute. Use this little bit of paper I used before. Let's see, pen. Right, so two force lines. We have a force line in this direction and a force line in this direction. So an equal opposite reaction is in these planes. So for example, in this parallel plane, horizontal plane, if you want to call it that. If we had equal opposite reaction on this plane, then it would cancel out. But the pivot point, which would be, say, a little camshaft or something, and we have our magnets, right, like this, and something like this. So the pivot point effectively would mean that when I adjust the pivot point so that it's pointing in this direction, any reverse equal opposite reaction would not be translated to cancellation. It would be against the actual point, if you understand what I'm saying. The actual point being a static point which can't move. So the only part that is moving is the rotational angle of the magnets. Right, so the rotational angle. So any equal opposite reaction will be directly thrust will be against the actual fixed pin. So it wouldn't cancel out any propulsion that we gain, because all I'm actually doing is rotating the magnet slightly. I hope you understand what I'm saying there, but this is just a demonstration on an idea I had, which is that just by putting this magnet here, it will repel slightly. You can see that. So when I bring it in the center, it will turn anti-clockwise now. If I stop this and bring the magnet on the outside, it will turn anti-clockwise as well. Except if you're on the end. If you're on the end, you're attracted to the steel, which is a dead spot, because I've neutralized the magnetic field mostly on the end keepers. So there's end keepers on here. So there's a certain amount of rejection on the entry point, which is why it's rejecting there. But the main drive force is in the central region, which is, I'll get the magnet out of my hand a minute because it's moving. So most of the forces, the drive forces, are between here and here. That's where most of the drive force is. The entry point has got steel, so it's going to repel or attract, because there's a certain amount of rejection on the entry point, and there's also a certain amount of reluctance, as in drag, on the exit point. But the overall midsection has more thrust than to overcome that entry and exit, but you've got to get past that point before you can start to get rotation. And what I was actually showing you is, to bring the magnet in now, is just by pivoting this magnet slightly, we can actually get this thing to spin around, but you need a certain amount of speed for it to start doing that. So once you get going, I just have to tilt it a little bit and it will accelerate, obviously, unless I hit the drag points, which are the entry and exit points. So let's spin it with my finger, get it going, and just pivot this, and you can see it will keep going as long as I keep away from the drag points, which are the entry and exit. So which is why I'm pivoting the magnet, is to reduce my drag on the entry, but I'm not having to move the magnet all the way around like before. I was previously had this in the middle like this, which will still do that. So if I have the magnet right in the middle, we can really get this thing to fly, just by spinning it slightly like this. But that's defeating the object. The main object is to show how much propulsion we can actually get from the outside with minimal interaction between the magnet. So we're only interacting with the magnet on 1 degree portion of the rotational circumference. So instead of using this in the center and pointing it 360 degrees all the way around, I'm basically using maybe a 5 degree point to give it a kick, a little push, and it's going. So yeah, which is really interesting for me, because that gives me some other ideas about how to make improvements to this. Because if we are able to directly, without moving the magnet around the circumference, the 360-degree circumference, if I can just get a field, a drive field, which is literally in one actual point, if I don't have enough segments. If I got more segments, I don't think I'll have a problem. It should, in theory, my theory is it should keep going. If I got more segments, that's why I'm waiting for more magnets. But with just one segment, just by pivoting this a tiny amount, I can keep it going, which is cool, because I couldn't do that. I could not do that before. There was too much drag. Last time, before I overcome a lot of the drag, when I pointed at the back end, it would just stall. It would just basically come to a stall. It would stick opposite over here somewhere. So you can see there's a difference. Now, if I stick a steel ball on this, what I really want is an array on the end of this magnet which is shaped so that it gets more of a push on at that latitude, well, not latitude, degree of angle, than it does on the entry point, so that the entry point doesn't give me too much of a cancellation. So we are definitely seeing an improvement on it, and I thought you'd be interested. Anyway, for Adrian Dax, for me, you were talking about me using my printer glass. Yeah, I did find it and I did try it, but the trouble was it slides around too much, and there's not enough friction at all, and it kept sliding sideways, which is what I don't want. And the only way to show this really is on the rotor system, which is what I'm using here. So I just stuck it back on the rotor and just to test the difference, and there's definitely an improvement on it. I think you can see yourself. I'm barely moving this magnet. I'm barely moving it. I'm only moving it a fraction, which is not significant, you know. Anyway, so do tell me what you think. Do you think this is something positive? Do you think this is a positive gain? I'm interested in positive comments. If you've got nothing positive to say, I don't want to know, because there's too much negativity in the world right now, and I do this as a hobby to keep my mind off negative things. As we all know, there's too much negativity with all this bloody virus and all that crap. So that's why I want positive comments. If you haven't got anything positive to say, just keep it to yourself, okay? Thank you.